So the second type of bonding for us to look at is known as covalent bonding. You'll see covalent bonding whenever you've got non-metals joining to each other or non-metals joining to themselves. So let's look at how a covalent bond actually forms. What we've got with non-metals is atoms that need to gain electrons to get a full outer shell. For example, I've drawn an atom of fluorine here, and just its outer shell of electrons, which has got 7. It needs 1 additional electron to get up to 8, which would be a full outer shell, which would be nice and stable. Whenever we did ionic bonding, we had a metal that transferred an electron to fluorine to give it the full outer shell, but in this case we don't have a metal to bond to, all we've got is fluorine. So what happens is we have a second atom of fluorine, which also needs to gain an electron to get a full outer shell. What these two fluorine atoms are able to do is share electrons. If they take these 2 electrons here and share them or overlap them together, what you'll end up with is this. So the 2 electrons they decide to share are now overlapping, and if you just look at each individual fluorine by itself, you'll see this left hand one has 1, 2, 3, 4, 5, 6, 7, 8 electrons. If you look at the one on the right by itself, it's also got 8 electrons. So by sharing this pair in the middle, we've allowed both fluorines to get a full outer shell, allowing them both to become stable. So sharing electrons is key to covalent bonding, and that's actually your definition of a covalent bond. A covalent bond is known as a shared pair of electrons. A couple of key features about this covalent bond is it's very strong, and therefore it takes a lot of energy to break that bond. So there's one example of a covalent bond, and to be more specific, the example we've looked at there is what's known as a single covalent bond. But there are other ways that covalent bonds can form, for example in oxygen. Now oxygen's got 6 electrons in its outer shell, and therefore needs 2 additional electrons to get a full outer shell. In this case, when 2 oxygens come towards each other, they'll actually share 2 pair of electrons. They're going to share this pair and this pair. And when they overlap, you end up with something that looks like this. So by sharing these 2 pairs of electrons, you've now got 4 in the overlap, or 2 pairs, and that still gives oxygen 8 in total. So 2, 4, 6 and 8, 2, 4, 6 and 8. So oxygen's now happy, it's got that stable full outer shell. In this case, because we've got 2 overlapping pairs of electrons, we refer to that as a double bond. You can also get examples of triple bonds, which you get with elements such as nitrogen. Now the 2 examples we've looked at so far have been for individual elements bonding to themselves, so fluorine bonding to itself, oxygen bonding to itself. You can get examples where you've got different non-metals joined to each other, for example in water. So the formula of water, as you should know, is H2O, which means you've got 2 hydrogen atoms and 1 oxygen atom. If we draw out our outer shell electrons for those atoms, oxygen's got 6, hydrogen's got 1 each. Therefore, to get everything with a full outer shell, this unpaired pair of electrons need to join up, and this unpaired pair of electrons also need to join up. If we look at the effect of that, the oxygen in the middle has now got 8 electrons, which is full outer shell. The hydrogens have only got 2, but remember the first shell only holds 2 electrons, so they are now complete and got full outer shells as well. Now here's just 3 examples of covalent molecules. There are other ones you need to know, which are contained in your notes. But again, the key idea is you're looking for electrons that are unpaired or need partners, and you're trying to pair them up to get everything with a partner and everything with a full outer shell. Now just a couple of definitions to go alongside these pictures. One is for what we mean by a molecule. A molecule is just 2 or more atoms covalently bonded together. So in other words, these 3 molecules we've got drawn out ahead of us, because they contain more than 1 atom and they are covalently bonded, they're referred to as a molecule. There is a more specific definition where you've got just 2 atoms covalently bonded together. Molecules like that are known as diatomic molecules. So here we see a slightly different definition. Diatomic is just for 2 atoms covalently bonded together. So fluorine here is diatomic, oxygen is diatomic, but the water molecule is not diatomic, it's just a molecule. One final definition is just within these diagrams here. We've already identified that the bits in the middle which are overlapping are known as covalent bonds. The pairs of electrons that are on the outside are known as lone pairs because they're not bonded to anything. So they're a pair of electrons by themselves known as a lone pair. So having looked at examples of covalent bonding through sharing electrons, we now need to look at covalent structure. Now the slightly tricky thing about covalent bonding is it's actually got 2 potential types of structure you need to look at. The 2 different types of structure are known as simple covalent and Jankovian. In terms of how you spot which one's which, it's reasonably easy to keep track of which one you're going to be using for different types of bonding, different types of covalent bonding. You will see Jankovian structures for only one element by itself, and that is carbon. So if you're asking the question about carbon, it's going to be Jankovian structure. Simple covalent will cover pretty much every other type of covalent bonding. So most things will be simple covalent, but carbon is the wee exception. It does Jankovian bonding, which we'll look at in a second. So in terms of simple covalent structures, simple covalent implies there's not really much to it, and that is true. When you've got simple covalent, you've got individual molecules that are separate from each other. For example, we've got a few molecules of fluorine beside each other, and we're just using a straight line to show a covalent bond, as we've got up above. In this case, the molecules are all entirely separate to each other, but there is a small amount of interaction between them. What we find is that we get very weak interactions which can take place between separate molecules. So the molecules aren't properly bonded to each other, it is just one fluorine bonded to one fluorine, but the individual molecules actually do get a wee bit of an interaction with ones beside them. There's a fancy scientific name for that force. It's known as an intermolecular force because it is between different molecules, and its other name is that it's known as a van der Waals force after the scientist who discovered it. The key thing about these forces between the molecules is that they are very weak and very easy to break. So if that's the structure for simple covalent molecules like fluorine and oxygen and water, let's look at the properties you get as a result of that. There are 3 properties you need to know for these structures. The first property is that simple covalent structures have got low melting points and boiling points. That is simply because to get something like this to melt or boil, all you actually need to break is the van der Waals forces. You don't need to break the strong covalent bonds. Just getting the molecules separate from each other will make your substance melt or boil. So they're low melting point and boiling point because you only need a small amount of energy to break the weak van der Waals forces. The second property is that they do not conduct electricity. If you remember with ionic bonding, we said that to conduct electricity you need something with a charge. In a simple covalent structure, you don't have anything with a positive or negative charge. Everything's entirely neutral, so it's impossible for you to get anything to conduct electricity. In other words, there are no charged particles. The final property you don't need to be able to explain. You just need to remember that in general, most simple covalent structures are not soluble in water. The second type of structure we need to look at is Jankovian structures, which at GCSE level you can think of it just being for carbon and carbon alone. With carbon, it's a bit unusual. Because it is able to form 4 covalent bonds from each carbon atom, you actually end up with quite big structures, much bigger than the ones we get with all the other nonmetals. Carbon can actually form 3 different structures. The 3 different structures are known as diamond, graphite and graphene. Diamond, graphite and graphene have got 3 different looking structures which you need to be able to recognise and spot in diagrams. There is a term used in chemistry whenever you've got the same element in a number of different forms. So remember, these are all just different forms of carbon. The name we use is allotropes, which means different forms of the same element in the same physical state. You do need to know a few key features of the structure and properties of diamond, graphite and graphene. So for diamond, the way we describe the structure is that each carbon is bonded to 4 others. That means that there's a lot of covalent bonds in the structure. That makes diamond very high melting point because you need a lot of energy to break apart all those individual covalent bonds, and also makes it very hard, again because you've a lot of energy needed to break those bonds apart. With diamond there's no charged particles, so no free electrons or ions, so it doesn't conduct electricity. The final thing you know about diamond is what it's used for, which is for cutting tools because it is so hard. Moving on to graphite, graphite's got a more unusual structure. What you end up with is these hexagonal rings in long layers, and there's weak forces going between layers. So all layers are separate, but they're kind of weakly attracted to each other. The way we describe the structure is that each carbon is bonded to 3 others with weak forces between those layers. Another feature of graphite is that this little ring we draw in the middle represents delocalized electrons which are able to move about, which impacts the properties of graphite. So graphite's properties, one property is it's got a high melting point because again it's got lots of strong covalent bonds taking a lot of energy to break. It also is very soft because the layers are able to slide over each other because there's only weak forces between layers. And another property is that because there is these delocalized electrons, it is able to conduct electricity. The final allotrope of carbon is graphene. Graphene is very similar to graphite. The only difference with graphene is that it's one single layer of hexagonal rings, not many layers like you get for graphite. So we describe that as a single atom thick layer of graphite. In terms of properties, it's got a high melting point because of all the strong covalent bonds. It's also very strong and very flexible because of those bonds. It's a good conductor because it's still got delocalized electrons. And in terms of what it's used for, it's got a lot of potential in use for batteries and solar cells. So to sum up what we've looked at here, we started with looking at how covalent bonding takes place in terms of electrons. They share electrons to get full outer shells. We looked at the two types of structure, simple covalent and Jankovian. Remember, simple covalent is just for most non-metals. We looked at the properties there. Jankovian, we got quite a lot of detail, but it's only just for one element, and it's for carbon, which got 3 different forms known as 3 different allotropes.